All right, I guess we can start. Thank you all for coming down today. Today's speaker is Peter, who earned his PhD in psychology at the University of Minnesota, and then worked as a postdoc at MIT in their Center for Brain and Cognitive Science. And now he's a research scientist at DeepMind, where he is a thought leader on graph networks, which is what he's going to be talking about today. So please welcome Peter today.
Thanks, and thanks for having me. Okay, so what I'll talk about today is some work that really was motivated actually by some work I had done with Josh Tenenbaum at MIT in cognitive psychology, studying how humans understand the physical world. But we really the main reason we were interested in those things was to try to get a better handle on good representations of the world in general, how the world works, how you understand complex systems, how you make predictions, draw inferences, control these types of systems. So when I joined DeepMind, my research sort of shifted more toward the machine learning end of the spectrum, away from kind of computational cognitive psychology. I've been very interested in developing machine learning models that can capture the dynamics or the rich sort of structure of everyday systems, and also hopefully systems that aren't everyday, like large scales and small scales. So that's kind of what I'll talk about today. I should let my cute video play while I was saying that. Okay, I'll show you how we made these types of. This is all coming out of a model that we trained, so I'll tell you how we did that. Okay, so I'll start off. So what's deep learning good at? Anyone know? No one knows.
Recognition.
What? Recognition. Okay.
Regression.
Oh, okay. Yeah, regression. Often like regression, classification in images, language. We've seen sort of stunning results in object recognition, machine translation, things like that. Also, games. So when deep learning was combined with reinforcement learning, we saw sort of a lot of rapid advances in what's been called deep reinforcement learning. And so the game of like Atari, Go, now StarCraft, games like this that are thought to be very complex games, our machine learning models can tackle and can exceed humans on now. But if you look closely, what these types of domains have in common is that I'll do this screen. You're giving the algorithm vectors, grids, or sequences. And if you look around at all the kind of big celebrated results in machine learning these days, this is, I would say, really kind of the lion's share of the types of data representation inputs that these types of approaches work on. But as hopefully it's pretty clear, this is pretty obvious to probably the people in this room, a lot of complex systems in the world are structured in different ways than vectors and grids and sequences. So you have molecular graphs, and you have everyday scenes can be described by scene graphs. Natural language is thought to be organized, or can be sort of parsed into trees. Code can be parsed into trees. You have phylogenetic trees. So normally what people do when they approach their problem with the sort of modern deep learning toolkit is they say, okay, like what's my data? My data is vectors. Okay, I'm going to use a multi-layer perceptron. I'm going to feed that vector into a perceptron. It's going to give either a vector output, a scalar output, something like that. Oh, my data is a grid. It's an image. Okay, convet time. Classify the objects. My data is a sequence, sentences, natural language. Recurrent neural networks are sort of the appropriate tool here. But the sort of big three in the deep learning toolkit really aren't that well suited to reasoning over structured representations, where there's not necessarily a natural order or a sort of Euclidean kind of geometry, things like that. So what we've been exploring, because we were sort of interested in a lot of systems that we don't think are well described as vectors and grids and sequences, we've been interested in neural networks that operate on graphs. So representing these systems as graphs, and then using tools that are sort of natively appropriate for operating on graphs. Okay, so I'm going to kind of go through just a little bit of background on graph neural networks, and then dive right into what we've done. So graph neural networks were this idea from really about 15 years ago or so. This is a nice overview paper on like the sort of early work. The basic idea, if you know what a convolutional neural network is, then you can sort of take that same logic where you're applying the same function to different regions of the image, and just think about it as the same function applied to different regions of a graph. So over here, these nodes over here, these edges over here are sort of can be processed by the same functions. So it's sort of convolutional over the graph structure. And to me, what the most important sort of element of what graph neural networks are really about is that what you're doing is you're learning to reason about entities and their relations. And a lot of what I'm going to kind of describe, and I think that it's one of the most important sort of aspects of dealing with graph neural networks, is thinking about what are my entities, like what are my objects, and what are the types of interactions that I want to compute over. So sort of you just figuring out how to fit your problem into graph structures, which end up being quite rich. So here, I can share these slides if anyone's interested. These are like links that you can click to see, to read up on some of the surveys. Okay, so what we've been developing and most interested in are a class of graph neural networks we call graph networks. And the natural question is, why do we need another graph neural network variant? So we designed graph networks. I'll sort of get into the meat of what's inside here in a second, but we designed them to be both expressive, sort of very like rich and flexible, but also easy to implement and work with. And what a graph network is a block. It's like a function approximator that takes as input a graph with some structure, and it can have attributes on the edges, that's EK, on the nodes, that's VI, or some global properties, which can be represented by U. You feed this graph into your graph network, and you get out a graph with the same structure, but with different attributes. That's what these primes signify. So now what I'm able to do is sort of learn some type of process on the graph. How does the graph's edge, node, and global state evolve through some process? Okay, and I won't describe what's inside the middle of here right now. I'll sort of like unpack that as I go along. But that's the key thing you have to understand, is that basically a graph network is a graph-to-graph function approximator. And when I said easy to implement, what we realize is you can kind of compose these graph networks just like ConvNets and MLPs and RNNs and stuff like that people do in modern deep learning. So you can have a graph network core. Actually, I guess in this case, these could be unshared. So these could be unshared graph networks. It takes a graph, an initial graph, outputs a graph, pass it to another block. You can kind of line up in series. You can also have a kind of recurrent or shared core that you do some learn message passing steps several times and then output a final graph. We often use what we call this encode, process, decode architecture, where we take some graph, we encode it with one graph network, we run some learn message passing steps with a different graph network, and then we decode the results. You can also do things like tracking the state of a system, so you have some kind of like hidden graph memory and inputs at different time steps. And graph networks, part of, again, to make, when I said we made them expressive and sort of flexible, we tried to think about a lot of the different graph neural network variants that exist in the literature and try to like unify them under one framework. So if you look closely, you can see that if this is a graph network block, and again, I'll describe the innards in a second, all of these other models in the literature, so like message passing neural networks, like interaction networks are one type, deep sets you might have heard about. We have this relation that's paper from a few years ago, or non-local neural networks, which are include the class of like transformer models that are very popular in NLP. They're basically like graph networks, but we've taken some of the internal components and just like removed them, and some of the wiring and removed it. But they can all be sort of like, this is a kind of superset of these models. Okay, so how do they work? So what am I talking about when I say learn message passing? So this is how we initially got into this. We were interested in trying to model the dynamics of physical systems that could be expressed as particle systems, like interacting particles or bodies. So in this work we had several years ago, we called it the interaction network. And the idea is that we're going to try to predict the dynamics in an n-body system or other physical systems by learning an interaction network, which is a type of graph network. So here's how it works. So we represent the states of the bodies as like their position and velocities as vertex or node features, VI, and any properties of their interactions or their relations with each other on the edge features between them. So the edges here signify that there's a potential interaction between these bodies. In this case, it would be gravity. We also will represent things like mass spring systems, where the springs are connecting the bodies, And then you would have a sparser graph. Not every body is connected to every other body. It's only those that have springs in between them. And in that case, the attributes of the edge could carry information like the spring constant, for instance. Okay, so again, the idea is you take what you care about, what are the entities, what are the relations, and try to map them into a graph structure that you can then optimize the parameters of to predict something that you care about. And here's how it works. So the graph network the first thing it has internally is a neural network phi e that we call the edge function, and it takes as input the edge attributes, an edge attribute vector, and a vector of receiving node attributes and sending node attributes. So this phi e is like kind of represented by this blue oval here. It's applied to the blue node, the purple node, and then the edge between them. And it's going to compute some function on these attributes. And we call those like this, you can kind of think of those as like message passing. It's computing some message. If the purple node is a directed graph, so it's like if the blue body is sending a message to the purple body, this is how you would compute that. You can think about these in a physical system as like force. You apply this, it's convolutional, so you apply this phi e function all over the graph to every edge and the bodies that are connected by the edge. And then you are going to update the bodies or the nodes by pooling their incoming messages. So you can sum up the messages E prime per body, I, and this E bar represents the aggregate messages that are like I as a body and receiving the forces. It's like force superposition sort of. And then we take those superposition forces or those aggregated messages, we take that vector, we also take each body's vector, vi, and maybe like some global property. Maybe it's like some kind of gravitational field or something like this. And we have a second function inside our graph network, it's phi v, and that computes a node update. So this is like kind of like the dynamics. It's like you can think of it as like an integrator or something like this. Okay, and that's basically it. So you are going to slide this node function over the graph as well, and compute, use the same function applied to all the different nodes, and then update the nodes accordingly. Okay, and what that gives you is a prediction about the future state of the system, or like the future state of the graph, and we're going to train that with supervised learning to just predict future states of this system. So the way we do it is we just take data of some n-body system, we simulate a big trajectory, we chop it up into pairs of states that are separated by some time step, and then we give as input to the model the initial time step state, and we predict as our supervised target the final state. And we can do this with, we tested this with 3 different systems, n-body gravitational systems, little balls bouncing around in a box, and these mass spring systems that also are kind of interacting, like, bumping into this kind of red rigid object you'll see in the videos in a second. The way we represent each of these systems is a graph. So here you've got all the bodies interacting, like, influencing other bodies. That's to reflect gravitational interactions. In the bouncing balls case, you also have interactions among other bodies because they can collide with each other. They're not always participating in a collision at every moment, but the fact that they can collide with each other is like sort of represented by the edge. We also have the walls in this are represented as nodes in the graph. They have edges that are only going out to the bodies because they can't be influenced by the body. They're like sort of static. And then we have this mass spring system. We have 2 kinds of edges represented by the different colors edges here. The green are supposed to be like spring edges that have properties like spring constant. And these black edges are like rigid interaction edges. So the red object can interact with any of the bodies in the string, but again, the bodies in the string only interact with their neighbors, and that's why there's only edges, like sort of sparser edges, just connecting the neighboring masses in the string. Okay, so that's how we set up our graph. That's how we represent the physical system that we're simulating. And then this is what it looks like after we train it. So the top row is a 1,000-step rollout from the true physics engine. So we initialize it with some initial. Let me see if I can stop it. So that would be like the initial conditions of the system. We feed that into the simulator, and we just kind of roll out 1,000 steps of trajectory. We do the same thing with the model. Now the model's only been trained to make 1-step predictions, so we're going to take its outputs and just feed the outputs back into itself as inputs and kind of let it hallucinate a 1,000-step trajectory. And again, so then you can look on the bottom row, that's the model's predicted rollouts, and they're very accurate. So especially in the n-body case, in the mass spring case, it's almost indistinguishable from the ground truth. What you notice in the bouncing balls example is that after some amount of time, it starts to kind of like not correspond that well to the ground truth simulation, but it still looks plausible, right? Error, like little glancing blows that happen, slight errors can accumulate very rapidly in this system. It's highly nonlinear. But the key thing is it looks plausible. And I should also say, like I always sort of say, I wrote this physics engine here, so like I don't know if this is very accurate either. It should be, but it's probably. My guess is that this probably has smaller error with respect to this, as this would have like a mainstream physics engine. But what's interesting again about these models is that because they're learning locally, like on the nodes and the edges, what this means is that the model doesn't really know about the whole system. It just knows about the kind of components of the system. So it's learning the kind of these emergent behaviors from the local interactions. That should appeal, I guess, a lot to the sort of physicists, which often, in physics, you're often thinking about reduced descriptions and trying to get the fine-grained things right to understand the behavior of the system at large. So here, what we've done is we've taken the same model that I trained from the previous slide, which had like 6 bodies, and I think it had 6 balls, and now there's 9 balls. And this one I think it was trained on 15 elements, and I think now there's 30. So we're just running this model trained on systems that are like half the size of these. We're just running them on bigger systems and seeing how they do, and they can, again, make very accurate rollout trajectories. So they're sort of generalizing both beyond the time steps they've been trained on, because they've only been trained on 1 step, but we're running them up to 1,000 steps, but they're also generalizing to larger systems than they've ever been trained on. So you're seeing a kind of like data efficiency here. We're training on small systems, short periods of time, and getting long time scale, large scale behavior. Okay, what I just described is that we're making kind of body-wise, like node-wise predictions. You can also make global predictions about the physical system. So what we also did was we created a sort of kind of augmented model that had one more neural network, this phi-u. And what this did was, sorry, I keep switching around here. The phi-u pools up, instead of producing output nodes and then like node attributes and then targeting them with supervised learning, what we do is we pool those up and then compute some function over all the aggregated node states. And here what we're going to do is target potential energy. So we're going to take the state of this physical system, and instead of training it to predict future time steps, we're going to train it to predict the potential energy of this system. Okay? And then these are the results for the n-body system and the mass spring system I showed you. The bouncing ball system, there's no potential energy. So in the n-body mass spring systems, the interaction networks, the blue bar, the MLP's performance, this is like mean squared error, so lower is better. You can see that if you kind of serialize the state of the system and put it into a standard multi-layer perceptron, it's like orders of magnitude worse in performance at predicting potential energy. And this is often what we see, that especially as systems get large, that the combinatorics and MLP, you've got to like figure out some serialization of your nodes, and then the MLP's got to learn that like that doesn't really matter, and it should be kind of invariant to any permutation. By construction, these graph neural networks and interaction networks are sort of permutation equivariant, and so they're much more data efficient in learning. The MLP would probably eventually learn potential energy, but you probably would just need like lots and lots more data, especially as you try to handle large systems. So does this make sense so far? So we can show that we can make predictions about the dynamics, like the kind of like body-wise predictions of the system, or global sort of properties of the system. We can also, like, what if we don't get the pristine states of the system? What if we get some kind of measurement of this? So to approximate this scenario, we did a second project where we took our interaction networks, but we prepended them with a convolutional neural network and fed in images instead of like x, y positions and velocities. So here you've just got some like colored balls bouncing around or connected by springs, and the convnet's job, which is kind of represented by this stack here, the convnet's job is to output first a set of node attributes, which are then fed into our interaction network, and we predict the states. So we do that. So here's our videos of these kind of bouncing ball and mass spring systems overlaid over, I guess, like these kind of image backgrounds to try to make it kind of visually complex or something. And left is the true, and on the right is the model's rollout. And to make these model rollouts, because the model takes an image as input but outputs states, we just render those states into images and feed that back into the model, and we kind of generate these hundreds of steps of rollout. I also put a note on here. We can even predict the states of objects that are not visible in this image because of how they influence objects that are visible. So sometimes what we would do is we would just make one of these objects invisible, and we would ask the model to predict its state, and we could do that because, again, it can see how the other ones are getting pushed around by that object. We've been sort of talking about, see if we try to find planet X in ways like this, right? And it's like, let's look, this is exactly what people do, right? Like, let's see the influence of these bodies on other things and see if we can kind of constrain down and figure out where things we can't directly see are. Okay, so that's kind of showing just how we can use this as like a regression technique. In recent work, what we've been doing, this is in collaboration with Shirley Ho's group at Flatiron Institute, is seeing if we can actually learn something about the underlying laws of the system. So here, this is a very complex schematic that Miles Cranley, who's very talented, made. But the key thing here is, this is again an interaction network. These little black things are supposed to, or gray things are supposed to represent vectors, the message vectors that I mentioned before from that phi function. He asked this question. He says, well, if those were like, if it's a 2D system, and you're saying these are kind of analogous, they carry the force information or the acceleration information, like, are they actually, could they represent actual force vectors? So we said, what if we just made these 2D vectors, like two-dimensional vectors for a 2D system, or three-dimensional vectors for a 3D system? Is it the force, like the force vector? So that I actually told him, I was like, I don't think that's going to work. Neural networks need big distributed vector representations, and he didn't listen to me, and he went and did it, and it worked great. So I'm happy to show you, even though. So this is what he did. So he basically, so actually, I think I probably, yeah. So he did two things. He looks at the vectors to analyze whether they actually are. There's some downstream linear operations. So what he does is he looks in to see if these like kind of size constrained vectors are consistent with like linear transformations on the true forces, and that's kind of what this data shows. So this is like the first, in the 2D case, this is the first component and the second component, and he's showing there's like a very tight relationship between the actual force law and the values on those on each of the vectors elements. And then what he does is he says, now if I sort of train my model and I rip out this message function here, this phi, and I actually do a symbolic regression on it, can I actually fit a symbolic expression to the force law? And he does. So he uses this sort of evolutionary algorithm, symbolic expression regression package. And what he gets out is that yes, he can. He actually recovers the force law that's been used to generate the simulations. So of course he generated the simulation, so he knew what the force law was. He tries this with several. I think he tries this with like 1 over r and 1 over r squared. But the exciting idea is that maybe we could do this with systems that we don't actually know the force laws for, or maybe we don't even know what the representation is. Maybe we just take some type of cloth or something and say we're going to make that a node and that a node, like kind of discretize it somehow, and then learn some function and then fit an actual symbolic expression to it that's like very compact and interpretable. So that's kind of exciting. And the reason that we did this, the whole point of the neural network part of it is to say, well, it's like, again, the inside of the neural network is supposed to represent in some way the like, it sort of is biased to have the same structure as what we think how classical mechanics works. So by having our neural network have these inductive biases that are kind of consistent with the physical formalism, we can then go in and take out the different components that correspond to things like forces and then try to interrogate them directly. Okay. And he'll actually, if you're interested, he'll present this at, and if you're at NeurIPS this year in Vancouver in a few weeks, he'll be presenting this at the physics, machine learning for physics workshop. Okay. Another thing that we've done recently in a sort of similar spirit is to try to impose more physics knowledge on our neural network architectures. Because the idea is like, well, sure, we can have some black box function approximator, but like, we know a lot from physics. Like we have good formalisms for describing, kind of a generic formalisms for describing a wide variety of complex systems. Let's use that instead of try to kind of like just ignore that and like learn through that. So here's my sort of schematic for how the setup for this project worked. If normally we get data, like this is kind of how data is generated. You have some system represented by a sort of position and momentum coordinate set, it goes into, like, this is how the world works. It goes into physics, and then physics steps forward in time, that's n+1, and you get a new state of the world. Okay, so that you can kind of think about physics as like a black box. What I've described so far is interaction network models, which now we've like renamed the delta graph networks to make them more obviously contrast with the thing that we were about to show you. Is the way they work is you take the like initial conditions, the Q and P. You also take some time step. Usually it's a fixed time step, so we don't actually even give it as input. You give it to some interaction network, some graph network, and what that predicts is like deltas, like changes in the position and momentum, for instance. I didn't say that before, but usually we predict like residuals, differences, rather than like absolute states. And we just predict the difference, and then we add it to the input, the initial conditions, and we get some new state. So this is kind of like an Euler integrator. Whoa, what happened? Oh, oh no. Uh-oh. It's on here. It's not good. Oh, okay. Okay, well, my builds are you're gonna have to imagine that you can't see this side of the figure. Okay, so what we actually normally do in simulators is we have this thing called an integrator. And what the integrator is it's basically a query mechanism against some data structure that's like the time derivatives in the differential equation that describes the system. Okay, so the way to think about integrator, right, is you take your integrator, you give it some function that like produces that describes the time derivatives. You also give it some initial conditions and a time step, and it returns to you the future. Okay, so what we can do is learn to approximate the function that we give to the integrator. And so this is kind of like, if this is like an ODE's time derivatives, represented by this f, we can just try to learn a function that goes from the initial conditions to the time derivatives. Now, we're not going to target this directly. What we're going to do is actually put this type of process in a neural network that's just, again, predicting future time steps. So instead of predicting time derivatives, we're going to predict future steps, okay, future states. So one thing we can do is use a graph neural network as a predictor of these time derivatives, and then in our our architecture, actually hand that to like an integrator, like a RK4 integrator or something, or an Euler integrator. Okay. Another thing we can do is put a further constraint. So this is a sort of constraint that says, oh, we think that there's a ODE that describes the dynamics of the system. We can actually adopt the Hamiltonian mechanical formalism and say, well, we're going to actually predict a scalar, and that's going to be an approximate Hamiltonian. We're going to take the gradients of that Hamiltonian with respect to the momentum and position coordinates, and then we're going to use Hamilton's equation to say that these are the time derivatives. Okay, so we can actually have our f be represented by everything in this yellow box here. And again, these are the only parameterizable. This is the parameterizable learned function approximator, but it's not parameterizing the time derivatives directly. It's parameterizing the Hamiltonian, and then we're using Hamiltonian mechanics to compute the time derivatives. Oh man. Okay, there's a rotating beach ball on my screen. I don't know what that means. Oh, come on now. I wonder if I should. Is it coming? Oh.
I'm not showing it.
It's showing my screen. Let's see here. My computer's getting hot or something. Wow.
Try a different connection.
Oh, it's like the timer even stopped. I don't think it's the connection. I think it's like my computer. I wonder if I have some kind of complicated thing happening in the background. No. I might just have to restart my computer.
If not, we can use the power.
Oh, that's right. We don't. I was about to show some videos. Okay, let's see if I can just restart this. Sorry about this. So we'll starting up. Does anyone have any questions about what I said so far?
How does cost of the machine learning method of integrating the equation scale compared to just solving the equation directly, given that you keep using the individual modes for integration?
How does the cost? Can you say it one more time?
I mean, in order for this to be worth doing, if you know the model you want to integrate in advance, then it has to be cheaper. That's my. I can tell I'm someone who's.
That's a good question. Yeah. So I think that there's many reasons why you'd want to learn a simulator, which and I'll kind of get to some of those in a minute. But I think your question is like for cases that I think for cases that you know the system, like why bother with any of this? Like we again we created these simulations. Like clearly it's possible to do without a neural network. So in that case, I think that one very important reason to try to learn simulations is because simulations can often be much faster. We haven't shown this that much yet. We're sort of working on these types of things right now. But I think the idea is that maybe we could like take a high res. We're actually talking about this a bunch a little bit. You take a physics engine with a high time resolution and like a very kind of small integration steps and maybe a high order integrator. Maybe you can kind of compute like a trajectory and then just kind of slice that into a strided, like a kind of low temporal resolution trajectory, and then try to train a neural network to predict those larger time steps, right? And I'll show actually just a little bit of that in a second if I get my, oops, going. So, so that's one reason that you would want to do it, but I can't really, I don't have results to show that that's actually a good idea right now, but we think it is. We're sort of working on that. Okay, I think we're good. Let's see. Okay, moment of truth. Yay, okay. So, so this is this is actually a sort of mass spring system that we constructed for this. The rest of these plots show one particle, one body that we pulled out just to kind of make it so it's not kind of a spaghetti mess. So this is like this is like basically integration with the true Hamiltonian. This is basically the analog of our interaction network that I was showing you before. So you can see over like many time steps, and I think that we probably didn't do quite as good of a job with this system as we did with the other ones, so that it does kind of decohere a little bit more from the ground truth. So that I think the blue is the ground truth and the red is the model prediction. You can see over like hundreds of time steps, it starts to kind of deviate a little bit. This is if we predict the time derivatives directly and then hand those to the integrator. So that like ODE graph network. And then this is if we use the Hamiltonian inductive bias, where we actually are predicting the Hamiltonian, taking the gradients of that with respect to the inputs, and then handing that to the integrator. And you can just see, like visually, it's much more stable over time. And like our quantitative results will show this too. I think this kind of shows this. So you can see like the predictive accuracy of the Hamiltonian graph network model in terms of the state. That's the red bar. It's like quite close to the true Hamiltonian. And we also measured like how accurate the energy is over time, and it's almost exactly what the true Hamiltonians is, even though we're using an RK4 integrator, not like a symplectic integrator. What's interesting is that actually predicting the time derivatives can actually have better energy accuracy with respect to the true system. I should say there's a difference between the true Hamiltonian and the ground truth system, because the ground truth system is like at a high. Actually, so I guess we're kind of getting at this question. We use a much finer time resolution to get the like ground truth, and then we make a larger time step, but use the true Hamiltonian. So of course there's going to be some error just because of the non-infinitesimal step sizes. These are meant to show that we also get some interesting properties in generalizing to time steps that we didn't train on. So because the integrator takes as input an argument that is a time step, what we can do is so we're like learning kind of like in some sense time invariant quantities. We're learning the time derivatives. When in the delta GN model, we're kind of like implicitly having it know the time step as part of its learning. So basically what this is showing is that like as we vary the time step at test time, from what it was during training time, which is the gray region, we get better generalization with our time derivative, ODE and Hamiltonian ODE models than the delta, the interaction network style models, which are the blue. This is, again, just a workshop paper. We're hoping to kind of do a little more complex systems with these and submit them to either a journal or a real conference. But if you're interested in your NeurIPS, come see our workshop poster at the, again, ML for Physics workshop. So again, this is kind of showing that you put more inductive biases and you can, again, hopefully generalize from a certain training regime to things that you didn't actually train on because you're getting something kind of fundamentally correct about the system. Okay. Let's see. So I just wanted to take one slide now. So the stuff I showed is mostly like these interaction networks. What we've been usually using more recently is what we call these graph networks, which are a little bit more general. So they kind of look very similar. We just now the edge blocks actually are conditioned on some global context. So if there's some global property of the system that you want all the forces to kind of be aware of, you can make that explicit. You can also have what we call a global block. So before we were like predicting the potential energy of that system, now we just we'll often kind of string together multiple graph network blocks and actually let them have some recurrent global memory about the system that's like this internal understanding of what's going on. And so it's basically just to say that we're kind of using a slightly more flexible class of models that we think is kind of the most general in this class. And so the rest of the stuff I'll talk about is kind of on that, using this. Okay, so we wanted to go from these kind of toy 2D systems and see if we could get how well these models worked on more complex systems, especially ones that are of interest to roboticists and kind of complex nonlinear dynamical systems people. So we had a project of an ICML paper from last summer, I think, where we took the DeepMind control suite, which is a bunch of simulated systems with this Mujoko physics engine that a lot of sort of robotic control people are interested in and use as a kind of benchmark for different types of prediction and control problems. So we're going to play the same game as we did in all of the previous stuff I just showed. We represent these complex systems now, like this. It's sort of like a two-dimensional cheetah, I think they call it, as a graph. So the bodies are the sort of of these things, and then they're connected by joints, which are the edges. So we represent the system as a graph. And we're going to do the same thing as we did before. We're going to predict the states of the bodies in future time steps. So here what we do is we actually compose together two graph network blocks with unshared weights. And this turned out to have a lot better performance than this kind of interaction network regime that we had been using. I think that the main take home is just if you have a much more complex system, you need more neural network capacity to approximate your internal functions. We also, we made explicit the difference between dynamic properties of the graph, like the position and velocity of the bodies, and the static properties, like their masses or like the length of the joints and things like this. So this is one of the systems, this swimmer 6, so this is like a swimmer with 6 links. It's in some fluid system, and basically what's happened, the reason it's moving is because there's random control inputs that are being imposed on it. So it's moving around because it's being actuated. This is a sort of typical way that you model things in robotics. And we do a pretty good job predicting the dynamics of these systems. But what's cool is that, again, because these graph neural networks don't really know about the structure of the system, we can train one model on a bunch of different systems. So the first thing we did was we took the model and we tried it on a pendulum and cart pole and this chaos pendulum it's called Acrobat, a swimmer 6, and a cheetah. So this is one model making predictions about all of these systems. So this is, again, the ground truth, the expected. This is the rollouts from the model. And you can see they're quite accurate. So, and then what we also did was we started seeing how it could generalize to systems that it had never been trained on. So here we trained it on swimmers with 3, 4, 5, 6, 8, and 9 links, and we tested it on 7-link swimmers and swimmers with 10 to 14 links. And you can see here's the performance, the generalization performance. So it had never been trained on these systems, but it can still predict their dynamics pretty accurately. We also showed that it works on real robot data. So in real, the simulation where you sort of have you have a fully observed state. In a real robot system, like these robot arms, you don't observe the full state. You get some joint angle measurements, but you don't actually know exactly what the state of the robotic system is. So these are just renderings of the robotic system. Like there was actually a real robot arm generated in the data, but just to show it, we rendered it. And you can see it's making pretty accurate predictions. One thing that was different was we actually used a recurrent graph network. So we actually let it kind of track the history over time, and we found that that works better. And I think it's because the state is not fully observable in these systems. It needs to kind of build up some understanding of what the underlying state is from observing what it can measure. And then we decided to kind of attack that more directly. So we actually wanted to say, in a lot of cases, you only get to see, the dynamic properties of the system. You don't know what the mass is, or maybe you don't know different properties that are influencing the dynamics, but are not directly measurable. So classically, in like sort of control theory, this would be called a system identification problem. You don't know what the problem, you don't know what the system is. You're going to try to make some inference about the state of the system so that you can then do your control. So on the left here, what I'm showing is basically but this is a pendulum that the model doesn't know the mass or the length of the pendulum's arm, which influence the dynamics. If the model is not given that information, it makes the same predictions for every pendulum. So when we vary the length of the pendulum, sorry, I'm doing it again, terrible. We vary the length of the pendulum arm, blue, green, and red. It has different dynamics. That's just these curves that kind of squiggle in different ways, but the model's prediction, the dotted lines are all the same. It doesn't know the difference because it can't observe them. But if we give it a little period of time ahead of time, before it has to make its predictions, we give it some, what we call like an ID phase, where we kind of poked and prodded the arm with, or the pendulum, with forces that the model could observe. It can sort of see how it reacts. So the analog here is if like you have no idea how heavy this is, maybe it's made out of stone, or maybe it's like hollow, and you see me kind of poke it with my finger, and it really doesn't go sliding away or whatever. You kind of get an idea for how heavy it is. And then if something else comes along and bumps it, you kind of know how it's going to move, basically. So what we do is, in front of our GraphNet prediction model, we prepend a little recurrent model that watches this poking and prodding period, and then it builds up an internal understanding of some information about that system that then it can use to make its downstream predictions. And this video, I apologize, isn't the most clear in how it's describing it, but basically these lines in the bottom are supposed to be like the ID phase, so it sees it kind of get poked and prodded like this, and then these are its predictions. Actually, so over here, these are the predictions over the long trajectory. So again, the point is here that it can, even if you don't have a fully observed system, but it gets to see how the system behaves under some external interactions, it can, in some cases, build up an understanding and make good predictions. Okay. Another reason, so in why would you want to learn simulation in general? Another reason you might want to learn simulation is because you can use it for inference. You can use it to solve inverse problems. So if you need to make inferences about the inputs or the underlying state of the system, or if you want to control the system, having a forward model can allow you to do that. So in the robotics and control literature, this is called model predictive control, but really this is like sort of inverse problems are everywhere in science and math and engineering. These graph neural networks are differentiable because they're neural networks. So you can actually backpropagate error gradients through them. Now, normally you backpropagate error gradients through a neural network to search for a configuration of the weights that are going to, optimize for your error objective. But what you can also do is backpropagate error gradients through the neural network to optimize control inputs. Okay. So what we can do is, so in this case, what we have is this robot arm. We've trained a forward model of this robot arm's dynamics. Then what we want to do is we want to control this arm. We want to choose a sequence of control inputs that will cause the robot arm that'll robot arm to match this target pose. Okay. So the way this works is we give it this target pose, and we initialize the robot arm to some random pose. We compute an error between the target pose and the random initialization, and then we compute error gradients and optimize. We search for a sequence of control inputs that will cause the arm to reach the target pose. And you can do this in. So we do this with the robot arm. We've also done this in a whole bunch of different systems. All the systems that I showed you, we've also done this like gradient-based control procedure, model control. You can also think about this again as a tool for doing inference. So what you could do is backpropagate error. Like if you get some, you have some system and you don't know what the initial conditions were, you don't know, say, like some hidden properties like mass, you could backpropagate error gradients from some random initialization, error between random initialization and some observations to optimize for the masses or the initial condition that would have given rise to your observation. Is that kind of clear? Does that make sense? Okay. And we do this with all the same things. We just run it on systems that we haven't trained on and that kind of thing. We can also try different, like a single model can support multiple reward functions. So this is just showing that a single forward model that we've trained on forward predictions can be used. We can compute errors with different functions and backpropagate those errors from different functions back in. And it kind of works okay. Like we didn't really work that hard on it. Do some kind of silly behavior here, but like, you know, it's increasing its verticality by standing on its head. But you can kind of see it's like trying to maximize its horizontal speed. It doesn't have arms. It's not that good at that, but it's definitely moving forward more than this one is. Okay, and this is one thing that this is the first time I'm showing this. It's sort of hot off the presses. So people often ask, like, okay, these 5, you've only got like 5 bodies or 12 bodies or whatever in these systems. Does this work in like larger, more complex systems? And so we've been kind of very interested in that. So very recently, what we started doing was seeing if we could model fluid simulation. So here we've got what we call this dam break simulation. It's going to be, it's kind of like water that we've colored in 4 different colors, like sort of like 4 colors of paint, you can think about it. And then we're going to just drop this on the floor and see, and it's going to be a sort of, it's not a smooth particle hydrodynamics, it's like a particle mesh approximation to the water splashing around. So here's the ground truth, and here's our model. And again, this is a much fancier version than I've seen before, in the sense that it's just got like more message passing steps and a bunch of kind of deep learning trickery inside, but it's really the same idea. So yeah, so you can see like it's pretty close to the ground truth. This is actually, I think, pretty good behavior. And really starting to get the kind of like splashing and weird structure from this. So we're going to try to submit this to something soon, I think. Oh, and this is funny. You see it stuck up at the top there? Okay, so we were like, oh, that's not good. And then we looked at the simulator, and sometimes that happens in the simulator. And we're like, okay, I think that's good, actually. So we need a better simulator. Okay. So the last thing I want to talk about is just pivoting a little bit to sort of what, like, I kind of mostly just shown, like, we can do, we can learn simulations and increasingly complex systems and kind of do fancier things with them. But now I want to sort of almost take like a bigger step away, kind of showing off the power of these models. So I like to kind of introduce this part by saying, I think that if aliens came down to Earth and they had to classify us, they would classify us as a construction species. They'd be like, this is a construction species. They build stuff. As a children, they start building stuff right away. They build like these beautiful architectural structures. They, build stuff in all kinds of climates and shelters. And even, they're not satisfied to just build stuff on land. They have to go up into space and build houses up there. So we're very good at construction. We're very good at like sort of putting things together and satisfying some functional objectives. And I think in many ways this is kind of one of the most crucial and kind of defining features of human intelligence. And I think that one of the evolutionary and kind of experiential motivations for construction, and sort of a lot of how our capacity for construction, in constructing equations and constructing proof for theorems and constructing whatever, all the things we build, comes from our capacity for intuitive physics and our reasoning about physics and how things interact with each other. This was sort of a lot of the work that we had done in cognitive psychology earlier, and sort of background I'm bringing to this. So we started to ask, like, how can we build agents that can build stuff? So we created what we called the construction environment, creatively named. And the way it works is you've got this floor, and you've got these blocks that you can move around and stack up and build things. And we're going to have a couple different tasks. And these red objects are obstacles. So these red objects are like things that your blocks shouldn't touch. And sometimes you have to like work around these blocks, and I'll describe that in a second. And you can kind of also think about this as like a Lego environment, because the agent's going to have the option to make the blocks sticky. So it can stack the blocks, or it can like snap them to the blocks below them. So it's just basically like a little Lego environment. So we've got several different tasks. I'll just put them all up and describe them. So the silhouette task is our simplest task. You're given some specification of what type of structure to build. That's like this kind of greenish silhouette. And then the agent's job is to grab blocks off the floor and stack them in those configurations. And you can see that sometimes it's like snapping the blocks together. That's what these little gray circles represent. It pays a small cost to snap them together. So we would prefer not to snap them together, but if it needs to snap them together, it'll pay for it. Also, I should note too that in these cases, the agent has an unlimited supply of blocks, so it can use as many of these blocks as it wants. It's like a sort of an infinite block vending machine. We have a connecting task, we call it, where instead of specifying the whole structure, it just gives a couple of different targets. We have to connect these blue things to the floor with blocks. Okay, so here you can see the agent's building some structures that like rise off from the floor and then connect to these blue things. I'll describe how all this works in a second. In the covering task, its job, this is kind of where it gets more interesting. It's like building a shelter. So the way to think about this is, it's going to rain. Don't let the red blocks get wet. So build a little, igloo or little houses around these red blocks. Okay. So we're not really telling it how to do it or where it even needs to go exactly. It just knows that it somehow needs to cover these up. And then we have a kind of, again, we're very creative. We're covering hard, which means that we're going to give it a finite supply of blocks. So once it starts placing blocks, it runs out of blocks, and it can't, it's got to kind of use them carefully, and it doesn't, we also put, we kind of put the red obstacles closer to each other, but this really requires kind of more longer range planning. So what we do is we build an agent, a reinforcement learning agent. The way it works is like this. It gets an observation of this scene, and we just give it, we've done a whole bunch of different things. I won't get into details, but here's the most relevant one. It gets a sort of symbolic representation of the scene. So it gets a graph that describes this scene. So you can see like these are the nodes of the graph, and like the A is that obstacle block, and the C is that block there, and the B is that block, and so on. And it gets, it's like what it can observe, and what it has to do is take actions such as place a block on another block, like place this D block with in the scene with respect to some other block. Okay, so it's again just like Legos. It's just like snap this block somewhere in the scene. The way it expresses, the way that its policy, the way it makes that decision is it computes on the edges of the graph. It makes some predictions about what snapping locations are best, the value of different snapping locations, or like with the expected value over the length of the little game. So if I snap this block here, that has better value than if I snap the block over there. Okay, and all it does, its policy, it just maximizes the value. So that white cell there is like is deemed to be the best place to place the D block. So that's what it chooses to do. So it takes the argmax over what are called the Q values, which are the action value functions in the sort of reinforcement learning terminology. We also have a version where so this one we just train with sort of model-free learning, just like people train, agents to play Atari or things like this. We also have a model-based version where it actually has a little model of the world inside its head, and it can do search. So it can search for, it can place blocks in its like imagination and kind of compute how good that, different structures are against each other, and then choose the immediate actions that will have are predicted to have better long-term rewards. And so again, the connection from this to the other stuff I showed is that the structure of the scene is represented as a structure object. Here, there's no like dynamics. We could train models of the dynamics, and we've sort of worked on this on the side a little bit. But here, the idea is that instead of having its knowledge about the system be expressed as how the system evolves in time, its knowledge is expressed as the value on different, on the structural relations between things in the scene. This isn't that important. This is just, I'll skip this. So here's some of the, here's the agents building. So the left is the agents that don't have relative actions. So these ones, I didn't really describe this, but this is kind of like the graph-based agent, and this is the agent whose actions are just kind of absolute. It's just like place an object in the scene, not with respect to another one. So what we're going to see is that the agent that is sort of making predictions about more kind of relational predictions makes much better structure across all of our experiments. So this is this connecting task, connected loop. I don't know what's going on here. And these, I should say, these are like our best agents that have like the absolute action. So sometimes they work. I don't know. They always just have this weird pathological behavior where they try to create like igloos over everything. You'll see that again here, I think. Yeah, more igloo. So these ones will tend to have lower cost constructions, like they can use fewer blocks and they can cover more of the obstacles and all this kind of stuff. And we also see that the agents that have, did I put it in here? Okay. The agents that, oops, hey, I'm supposed to use video here. Yeah, so the agents that can plan, so I mentioned briefly that we have agents that actually have a world model and can plan with it, are more accurate and can make better construction. So that's this like heavy purple line here. And this is actually, it looks like a small amount of reward, it's actually a huge amount of reward. So these end up, this is like the difference between making like kind of mediocre structures, so like almost like what we think are kind of optimal construction. Okay, so I'm basically almost out of time, so I'm almost done. Okay, so that's basically the end of the research talk. So it's sort of, again, saying like, here's how we can learn kind of structured models of physics and then use them for kind of interesting kind of control and decision-making problems. If you're interested in playing with our code, everyone's phones go, okay. Yeah, so we have this GitHub repo with our GraphX library. Like, all the stuff that I've shown is basically made in that library. Not all of it's online, but we've got kind of like demos of kind of the simpler stuff. It's really easy to use if you use TensorFlow. I think, is Battaglia here? Oh, there, okay, good. So if you want a PyTorch version, talk to him. Yeah, so it can implement all of these different models that I was saying before, if you're interested in them. And you've got some demos. You've got some like Jupyter Notebook demos that it's all basically the same model too. Like it's doing shortest path on the graph. It's just sorting elements in a list. Or you also have your little physical prediction demo. This is kind of predicting the dynamics of a mass spring system. It doesn't look that good, but we are like constraints on these demos with that they should train in your Colab notebook in like 5 or 10 minutes. So this is what you get if you train for like 10 minutes in Colab. So if you increase the capacity of this model and make it more powerful, it'll be very, very accurate. And so that's it. So that's my conclusions are basically graphical networks should be first-class member of the deep learning toolkit. Like move over MLPs and COMNETs and RNNs. If you have structured data, structured patterns of reasoning that you're trying to approximate, you want graphical networks. They support simulation and other types of structured, control and decision making. And something that I'm very excited about now is, trying to think about, like I showed a little bit about how we're interpreting what's been learned. When you have a kind of more richer internal structure and inductive biases within your model, you have more room to interpret what you've learned. So a big sort of critique of modern deep learning is that it's often very black box. We don't know what's really going on, this and that. I think that if you can start to impose more constraints and things like that on your architectures, you kind of know what the different pieces are supposed to be doing, and it gives you a more like kind of modular and direct access to the different components of the computation that's being learned. That's it. And these are like all my collaborators who I'm very thankful for.
How much do you think that some of this might be applicable to real data? In the sense that, let's say, for the model that's up to volts that are bouncing around, let's say give you a few videos of a billion come from above, you don't have access to the real kinematic information you have to extract it from the video. Do you think there's a way of getting a model trained on this kind of data that would be able to do well, or is there some limits to?
So, I think in the case of visual scenes, I think it's going to be. I think this is the way to go. I mean, that's why I'm doing this ultimately, because I think that human beings, when we open our eyes, and animals, we understand the world in terms of objects and their interactions. I think that's, in many ways what gives us our kind of power is like our data efficiency of learning and our combinatorial generalization. But everyday scenes are very complex, and I think that you're going to see like, so I would call this like in the general class of structural inference. Like, so if a lot of what I show is structural reasoning, it's like you have some structure, you're going to reason about the structure and like make predictions. There's like inference or induction. It's like is unstructured to structured, right? I have like an image and I want to turn it into a set of objects with relations. I want to like transform from a kind of less structured to a more highly structured. I think in everyday scenes it's a very challenging, important problem, but I mean, we'll eventually make progress, but I'm not sure if this isn't like the answer. This is like the what maybe like this is the thing that comes afterwards that incentivizes an upstream system to decompose the world into objects.
And I guess like if you have like a video of billiard balls bouncing around, you can come up with some algorithm to extract like the momentum.
Yeah, I mean billiards.
You have like some error on it. So how much would that like?
If you like, I mean, there's definitely algorithms now that can segment billiard balls. Like I'm sure that these would work just fine on those types of like if you had an algorithm that segmented the image into billiard balls, I'm sure this would work fine because the stuff we show with bouncing balls it should be very similar to billiards.
Yeah, so you think it would work quite well?
I think that I think the dynamics of real systems. Okay, so I was taking more of like the image side. Yeah, so I think the dynamics of the real system. Yeah, we've done this in the robot arms again. Like these fluid systems are like quite sophisticated. Like these are not, these are like hot. I did not write that physics engine. I think it should scale. Like I think, again, these are all questions of just sort of how well can you approximate some complex thing. I mean. We're very interested in that now. I can't say that it will, but I expect it to. But the question of how to take the raw observations and turn them into a structured representation, I think is very challenging. I'm not sure. Again, in some things, it's just not even clear what to do. Like, how do you, like, what is the object? If I take this thing, what is the graph of this? Like, right? I mean, in graphics, they do use like, mass spring mesh methods, but there's a lot of choices that go into that. So I think very interesting question is how to approximate this as a graph or whatever. Or should you? Maybe that's not the best way to do it.
Question on this side.
So we are interested in the heart. And the question is whether you have looked at multi-scale systems where you are trying to simulate, so we're simulating that deformation, but we want to incorporate some knowledge of what happens at the subcellular level. Whether you have dealt with hybrid models that would have physical detail, but also kind of a deep learning model attached to it.
Right. So mostly what I've talked about again was like sort of things that if you like, I was trying to say at the beginning. I guess I sort of said it again. There's a really important question of how to take your problem and represent it as entities and relations. And if you can't, if that's like not really the right way to do it, then you wouldn't like probably this is the first.
But the question is whether you have dealt with this or not. Whether there is an example where you've dealt with multiple scales and different types of models. Or
We're thinking about this a lot right now. I don't think that there's been that many good examples of this. People are definitely trying to build these kind of hierarchical graph networks and things like that. We are too. Sometimes we find that it doesn't actually help that much when we really, like, even in that stuff I showed with the fluids, like the color thing, we kind of started off doing like these we need hierarchies for all this stuff, and actually, that doesn't have any hierarchy. So, but there's an important thing, which is that, okay, so I think that hierarchy and abstraction, things like this, will have. So it sounds like what you're talking about. You're actually thinking about like you're interested in the heart, and you want to try to have it be informed by the lower level stuff.
Good or not.
Yeah, I mean, there's no reason that you can't create like bipartite graphs, or like even a lot of people are trying to come up with these schemes of like around a kind of fine grained message passing and then some coarser grained message passing. I'm not. I guess the thing I was going to say was that often I think that when you do many rounds of kind of message passing, that allows you to approximate kind of longer range, more global coarse-grained properties. So that's why I think we often don't really end up needing hierarchies. But again, I think what you're asking about is, I think, integration on different scales, and I don't think we've thought of that. Maybe we could talk offline.
Sure.
Yeah.
So in all your examples, you showed kinds of systems which are super homogeneous. So each node is similar to the other. What happens if we have nodes which are different? What I mean by this is they have different features. So we can pad so that the corresponding features are in the same place, but this is going to be problematic if the simulators speak of a number of different entities.
Yeah. Similar to the answer I was just giving. So often, like in the interaction or stuff, we had the case where like the mass spring system, and it also had rigid interactions. And there we first, so you can think about typed edges, like different types of interactions. That's one way to, like one example. We tried that at first. It just didn't really help over just using a single edge function where we gave as input on the edge attributes, like this is a spring or this is a rigid interaction edge. These graph networks support like multi-graphs, so you can have like more than one edge between things even. So if it has like if two things have. So what I would say is that, and also there are people, there's a bunch of work people who are like trying to have kind of, you can almost think about them as like multiple graph networks that where you have, I mean it's basically just like, basically if you have two classes of nodes, like you have you know, words and documents. You can put like 3 types of edges, like inter-word edges, inter-document edges, and then word-to-document edges. And you could have those with different node update functions or edge update functions. There's nothing wrong with that. Like you just, you know, that's easy. It's like a conditional statement in TensorFlow or something. Sometimes people do this all in parallel, or sometimes they're doing it more as like a kind of iterated thing, like communicate among the words, communicate among the documents, communicate back and forth to each other. This is sort of into this question too. We haven't really worked with that stuff that much, just because like we just don't really find we need it usually for the types of problems. They are homogeneous systems, so I think you can. Again, those phi e and phi v and stuff can just be indexed by a type, which I think is basically what you're saying.
Yes and no. Let's say in your pockets you might have different amount of objects. Every person here has different amount of objects in his pockets. So you can't even represent that when you have a variable number of these features. So you can process any graph topology, but their feature dimensionality should be the same.
If you have a set of things and you don't know the number of things, then you might need a graph network for each pocket. I mean, that's always my answer. Like, if you have variable numbers of stuff, you want something that's able to handle variable sized things.
I think you mentioned this in the paper when you said that the global component might be a graph net, and it itself might be a graph.
Yeah, you can. I mean, yeah, there's nothing that we did. Probably a moment of slight like over ambition. We were like, why don't we make the library very flexible so that the phi-e's can actually take as inputs graphs. So it's again, it's like a graph network that operates on graph features. And we were like, no one's going to use that. Maybe we should have done that. But you can just write it yourself, and then you'll have it.
So many physical systems are actually chaotic in nature in the sense that they're sensitive to initial conditions. Have you noticed that your learned models also behave in similar ways? In the sense that they don't overfit to the trajectory seen at training, but actually you just take the trajectory that you had at training, the initial conditions, perturb them a little bit, and get significantly different behavior from the prediction as well?
Oh, they definitely do. Like I mean, if you perturb like in like the n body and stuff, the bouncing ball is even worse. Like there is a tiny bit of error in the model still, right? Like even though we get the one-step error very, very low, like all it needs to do is make a little bit of error, and then just all it needs to do is have two objects have a glancing blow with each other. The system's it goes in a completely different direction as the true. So they're because the error is so low, and when we train them, we know that they're very sensitive to, if the system has complex dynamics, or it's chaotic or highly nonlinear, then we know that it's going to be very sensitive to the initial conditions. But there's another point here, I think is what you're saying I didn't address, which is a lot of systems, it doesn't really make sense to talk about a trajectory. Like it's chaotic and our measurements are only so good, so it's really like a stochastic thing. So you see this a lot in like molecular dynamics. Like it's not really clear what like the trajectory. I mean, you think about time averaged quantities, and we've been starting to think about that more, like either predicting distributions over the state rather than actual point estimates of the state, or instead of even predicting distributions over distributions where the event space is the state, like distributions or statistics on things like the total energy or the free energy or the, like radial distribution function, things like this. So I guess I would say that if it makes sense to think about the deterministic dynamics, I mean, there's always some approximation error. We just measure it. Like, we just measure how well it's sort of faithful to the true thing and how sensitive it is to initial conditions. But I think there's a bigger question, which is what about situations where it doesn't make sense to try to think about a deterministic trajectory as much as like other coarser grain properties.
We'll take that as the last question before we continue.
You mentioned near the beginning that the networks were learning emergent behavior as well as the sort of small time step dynamics, and I guess that was related to the comment you made later about being able to take larger time steps than the ones that you trained on. Can you say anything more about interpretability in that context?
Yes, that's a great question. So we'd love to know that, right? So like the example I use is like, okay, so if you have like one body, a small body orbiting a large body, you have this thing called an orbit. There's no orbits in here, right? This is just like step, step, step. But maybe a better representation of an n-body system is as a set of orbits that are like interacting, and that's kind of how in my very limited understanding of kind of orbital mechanics, this is like, we often think of things as like, the time step is the orbit, basically, interacting orbits. So you could imagine, so one thing that we have, I didn't say this, but in the visual interaction network work, and we played with this, other people have started to play with this a little bit, having multi-scale, multi-time scales. So like you have a kind of fine-grained time scale, and then you also have like a long-range time scale. And the idea is that you're going to be like predicting, and you could even imagine having these, so again, like in the orbit example, maybe you would have something that takes steps that are about the length of an average, about a year long or something. And maybe what you're actually learning at that level is about how orbits interact with each other. Or you could even try to do like time averaging of the low level, compute like a feature that carries information about a whole year, and then see how the like orbit object interacts with other orbit objects. I think it's a very interesting question. So like, we see kind of emergent, we see like the more large scale phenomena because we get the low level right, but I think it'd be very interesting to move away from the kind of standard reductionism to learn macro scale theories, like why are galaxies, there's like 3 types of galaxies, of like shapes, spiral and elliptical, and I don't know what the other one is, someone will say. So like what, there's very, just like clear high level structure everywhere. So it would be great to have theories of that. So we're thinking about that, but we don't know how to do it. If you have ideas, please.
So that's it. Thank Peter again.